The spanning tree protocol is a layer 2 networking protocol that's used to prevent switching loops and broadcast storms. Switching loops occur when there's more than one physical pathway between network switches, or when two ports on the same switch are connected to one another. Having these physical connections will cause broadcast and multicast traffic to begin looping around the network, building up a storm known as a broadcast storm, eventually exhausting the resources of the network switches and causing the network to fail. A broadcast is when a datagram message is sent from a host device to the network. The switch will create a copy of the datagram, then flood that message out to all switch ports, except the port that the message originated from, that are within the same broadcast domain as the sending device. In other words, the broadcast will not traverse a VLAN. This is known as a one-to-all association. An example of a broadcast message is when a host device is building an ARP table which resolves the IP address to the MAC address. It will broadcast to the network with its MAC address as the source, and the destination will be a block of Fs, which is received by another host. The block of Fs are replaced by the receiving host's MAC address and returned to the original sending host to build the ARP table. Multicast is when data is sent to selective destinations based on a multicast group, so the data isn't flooded out to the network. Devices associated with the multicast address will receive the data. This is known as a one-to-many or many-to-many association. The addresses will range from the values displayed now. So a host device transmits a broadcast. The broadcast datagram then gets copied by the switch and flooded out to the other ports. And if there's an additional switch connected downstream, that switch will receive the broadcast, create a copy, and send the broadcast message out to all the switch ports. And if there's another cable connecting those switches together, the broadcast will be sent to that port and back to the original switch, copied and sent around again, along with the original broadcast, and this will keep repeating itself and looping indefinitely. The header in a layer 2 frame does not contain a time to live value, unlike layer 3 packet headers. Every time an IP packet hits the router, the time to live value is reduced by 1. So if a packet is looped, eventually it will be dropped because the time to live has reached 0. The layer 2 frame will continue to loop around the network indefinitely until
computer says no.
Switching loops can also cause MAC table instability. Receiving the same broadcast on 2 different ports will cause the MAC table to associate a MAC address to 2 different ports and may cause traffic to be directed to the wrong port, causing it to be lost. How can we prevent switching loops or even plan our network to allow for multiple connections between switches? But 1 minute, I just explained why multiple connections are bad between switches, didn't I? Well, yes I did. But you can plan a network to have multiple interconnections between switches. This may be for link aggregation or redundancy. Link aggregation is the protocol to use 2 or more ports on a switch to expand the throughput between switches. So having 2 1 gigabit links will increase the data throughput than just having the single 1 gigabit link. I've got a video on link aggregation which explains all about it. But if we were to use multiple interconnections for redundancy, we need to use the spanning tree protocol. So first of all, what is redundancy? Redundancy is a fail-safe option to keep a network up in the event of failure. For example, you have a core network switch. From that switch is a single connection to another switch. What if someone cuts through that cable or the switch port fails? Then communication will be lost. Redundancy is a redundant path that will come into play in such an event. So having a second or third connection between those switches will provide backup connections between the switches, thus keeping the network up. You can also do a similar thing with routers, but that's called high availability, and that's another video. Spanning tree allows us to set up redundant paths without creating a switching loop. It monitors all network connections, identifies the redundant paths, and disables those ports to avoid loops. But let's find out how it works. When configuring spanning tree, there are a few considerations to take into account. Spanning tree is not a protocol you just switch on. First of all, we need to decide what switch is going to be the root bridge, the core switch, and everything is going back to. The root bridge is decided by the lowest bid, or bridge ID. This is made up of 2 parts, the priority and the MAC address. By default, Priority is usually 32,768. So when you get a switch out of the box and plug it in, all those switches have a default priority of 32,768. They're all the same, so no root priority is set. So the root then gets elected by MAC address. If we had 3 switches, let's say these switches with the MAC addresses ended in a block of 1s, a block of 2s and a block of 3s. The lowest value MAC address is D46A91111111, so it would be elected as the root bridge. However, if you solely rely on the network electing a root bridge, then you could end up with a device acting as a root bridge that's not designed to be a root bridge, due to them either having a lower value MAC address or priority. A host device that's known for electing itself as a root bridge when it shouldn't be is the UK satellite provider Sky. If we log into my 8-port Arachnid switch and go to the spanning tree configuration, we can see the root bridge is not the MAC address of the 8-port switch itself. It's that of the Sky Cube box that I have, which is not what I want. Not because of the MAC address value, but the priority. The Sky box has a value of 28,672, so something to look out for there. I should set my 8-port Arachnid switch to be the root with a value of 4,096, the lowest value, hence making it the root bridge. My network setup is a little bit different. I've got a 24-port switch on LAN port 1 on my router, and my 8-port switch comes off LAN port 2 on my router because I turn my 24-port switch off at night and the 8-port switch stays on because they run my house. So the 2 switches are separated, but that's why my Skybox has elected itself as root bridge on this collision domain. Next in the setup, we want to elect a root port. This is based on costs. The root port is the single port that will be used as the pathway back to the root bridge. The cost determines the closest bridge to the root based on cost values. The lower the cost, the faster the link back to the root bridge is. The path cost values on a common Ethernet network are for 10 megabits 100, for 100 megabits 19, for 1 gigabit 4, for 10 gigabits 2, for 40 and 100 gigabits is a cost value of 1. These are the short path costs. But there are also long path costs, which are becoming more used because of the speeds that networks can reach now. So 10 megabits per second is 2 million, 100 megabits per second is 200,000, 1 gigabit per second is 20,000, and 10 gigabits is 2,000. If you need to work it out, take 20 terabits. I converted it to megabits, so 20 million, and divide by the port speed. Again, I did it in megabits, so 20 million divided by 1,000 megabits, which is 1 gig, equals 20,000. Anyway, that's the 2 methods. So how is this used to determine the path to the root bridge? Well, in the current networking world, 1 gigabit ports are pretty much a standard, but there's now also 10 gigabit ports and 40 gigabit ports. 1 gigabit is a cost of 4. 4 was chosen to ensure backwards compatibility with older versions of spanning tree. Let's take a look at a simple topology. You have a few network switches, switch A, which is the root bridge, with a priority of 4096, switch B and switch C, which are secondaries, with the default priority of 32768. Switch A is connected to switch B and C. But there's also a link between switch B and switch C. Now, if we left this as is, we've created a loop, and the effects of a loop are what I explained earlier, so we need to work out the costs. The connection between switch B to switch A is 1 hop, so it would be a cost of 4. The same goes to switch C to switch A. This also has 1 hop, so it would also be a cost of 4. Then we have the connection between switch B and C. Switch B to C is a cost of 4, and then switch C to A is another cost of 4, which is 8. So has a higher cost and a longer route back to the root bridge switch A. And the same for the reverse, switch C, switch B, and back to A is a cost of 8. So the ports that have the lowest cost back to the root bridge have the shortest path and are elected as root ports. The root bridge doesn't have a root port because it's the root. The ports that are outbound to secondary switches are elected as designated ports. Then there's the link between switch B and switch C. The cost between these switches is 4, so they are the same. They're both a 1 gigabit connection, so the switch with the lowest bid is elected. If switch B had the lower priority, say 8192, then that switch port would be the designated port to switch C. If the priority was tied to both switches at 32768, then the lowest MAC address is elected. Switch B is the lowest MAC address value, so the port connecting switch B to C is designated port, and the port connecting switch C to switch B will be set to a blocking state. The port is enabled and ready to pass traffic, but blocking that traffic from passing through the link until required to do so. So we may now have a bit more of an understanding on why SkyQ boxes at present set themselves to be a root bridge. Out of the box, they set their priority to 28,672, so already lower than most switches out of the box. The UHD boxes also have a gigabit Ethernet port, so they'll also have a low cost value. So let's take a look at another example of a looped topology and work out what ports are designated ports, root ports, and blocking ports. In this example, we have 4 switches, switch A, B, C, and D. Port 24 on switch A is connected to port 24 on switch B over a 10 gigabit fiber link. Port 23 on switch A is connected to port 24 on switch C over a 10 gig fiber link as well. And port 22 on switch A is connected to port 24 on switch D over another 10 gigabit fiber link. On switch B, port 23 is connected to port 23 on switch C over a 1 gigabit copper link. Then port 22 on switch C is connected to port 23 on switch D, also over a 1 gigabit copper link. The first thing to work out is the root bridge, so which switch has the lowest bid. Switch A has a priority of 4096, so is elected as the root bridge. Switch A would still be the root bridge because it has the lowest value MAC address. Now we need to work out the root ports on switch B, C, and D. Let's start with switch B. It has 2 paths to get back to the root bridge, directly from B to A or via switch C. The cost from B to A would be 2 on a 10 gigabit link. The cost to go from B to C would be 4, and then C to A another 2, totaling 6. So B to A is the lowest cost, and therefore port 24 on switch B is the root port. How about switch C? This switch has 3 paths to get back to the root bridge: C to A, or we can go via D, or via B. The cost to go from C to A on a 10 gigabit link is 2. C to A via B is 4 plus 2, which equals 6. And C to A via D is also 4 and 2, which equals 6. Port 24 on switch C is the root port. And port 24 on switch D is the root port. So we have our root ports, ports 24 on B, C, and D from switch A. Remember, the root bridge does not have root ports because it's the root bridge. Instead, it has designated ports. Every switch connected to the root bridge is the designated port. The other links between the switches, B, C, and D, will either be designated ports or blocking ports. Let's take the link between B and C to get back to A. To go from switch B to A via C is a cost of 6. To go from switch C to A via B is also a cost of 6, so we have a tie in terms of the cost. So we then use the lowest bid to determine which switch is the designated port. Both switch B and C are both using the same priority value of 32,768, so we go on the lowest MAC address, which is switch B. So port 23 on switch B is the designated port. Now we have switch D to C. The cost to get from D to C is 4 over the 1 gigabit link, but then to get from C to A is a cost of 2. So switch port 22 on switch C is also a designated port because it has a lower cost to get back to the root bridge, switch A. The final state of the leftover ports will be blocking, so the link from switch C, port 23 to B will be a blocking state, and then the link from switch D, port 23 to C will also be blocking. So we can now see the loop-free connections between the switches and the redundant links should there be a failure. So how does it all work then? When a link goes down between switches, how does it know to kick in? Let's go ahead and answer that question. Let's go back to the really simple example before. we've got the three switches A, B and C. Switch A is the root bridge. On port 24 is a link to switch B, port 24. On port 23 is a link to port 24 on switch C. Switch port 23 on switch B is linked to switch port 23 on switch C. Our root bridge switch, ports 23 and 24 are designated ports. Port 24 on switch B and C are the root ports back to switch A. Port 23 on switch B is a designated port to switch C, where port 23 on switch C is a blocking state. If the link between switch B and A were to fail, spanning tree won't kick in immediately. Switch C, port 23 will remain in a blocking state for about 20 seconds, waiting for BPDUs or Bridge Protocol Data Units from switch A. BPDU plays an important role in spanning tree. They are used to periodically check the network topology and adapt to any changes by exchanging messages between switches to gather the information on the spanning tree configuration and carry information about the path cost back to the root bridge. They're sent out on a multicast address. A root bridge uses a configuration BPDU to provide all the switches on the network with the spanning tree information. And the other switches will send a TCN or topology change notification to the root bridge to inform if a port is up or down. If the switch port doesn't receive BPDUs after 20 seconds, the port then changes its state from a blocking to listening state. It doesn't pass traffic straight away, it needs to be sure there is a link failure somewhere. The port will listen for 15 seconds. It's listening out for BPDUs on the other interfaces. Once it sees the BPDUs on the other interface, the port transitions from a listening state to a learning state for another 15 seconds, where the port is learning to repopulate the MAC address table. After the port changes from blocking to listening to learning, it finally opens up and allows traffic to pass through, which is called forwarding. When the link between B and A was repaired or reconnected, then the switch will reevaluate its costs and reinstate the original port as the root port and put the temporary root port back into a blocking state. This is based on standard spanning tree protocol. We have other versions of spanning tree such as rapid spanning tree protocol or RSTP, multiple spanning tree protocol which is MSTP, and common spanning tree protocol or CST. This common spanning tree allows multiple VLANs to share a single spanning tree instead of configuring a spanning tree per VLAN, and can reduce the number of ports that are blocking. So if you had VLANs 11, 12, 13 and 14, whatever you use, they will all use the same spanning tree and the same root bridge. MSTP, or the multiple spanning tree protocol, is configured to allow VLANs to use different switches as root bridges, which would help that LAN have better performance. So if you had VLANs 10, 11 and 12 on switch A and 20 on switch B, then you might find that VLAN 20 will benefit from having the root bridge set to switch B. CST and MST both use the same time to set the port from blocking through to forwarding. So we have RSTP, the rapid spanning tree protocol. This can change the state of a port within a couple of seconds, if not faster. Each switch works together to provide a faster convergence using the root ports and designated ports to determine lowest path costs and best paths to reach the root bridge. In spanning tree we have the terminology blocking ports, whereas in rapid spanning tree we have discarding ports. We also have alternate ports, which monitors the state of designated ports and can change the alternate port state almost immediately should a switch's designated port fail. We need to be aware that although RSTP is backwards compatible, it might not be supported on some older switches where only STP is supported. Let's take a look at a simple setup in a demonstration. I've got my Arachnus 210 SW24 PoE network switch here, and this is my root bridge. Then I have an Arachnus 310 SW 8 port PoE switch, which is my secondary. On the 24 port switch, port 11 and 13 is connected to my 8 port switch. There's no reason why I'm using these particular ports, just random ports I used. I log into the 24 port switch, the root bridge, and go to advanced, STP and global settings. By default, spanning tree is enabled. The first section we have is the root bridge information. This information here relates to the basic settings below, but we'll come to that shortly. We have the root address. This should be the MAC address of the root bridge. So the network switch I'm currently logged into. My 8-port switch showed the skybox, which is not correct, so make sure the root bridge is in fact the root bridge. Then we have the priority, which I've already set to 4096. In the drop down below, we have values that go up in multiples of 4096. The lower the value, the higher the priority. If the switches are left on default priority, so 32,768, then the lowest value MAC address will be elected as root bridge. The cost is 0. This is the root bridge, so there's no cost. Port is the switch port linking to the root device. Don't forget, the root bridges do not have root ports. They use designated ports, so this will be blank on the root bridge. Forward delay is the amount of seconds before the root bridge builds its bridge table after the maximum age has passed. This is 15 seconds by default. The maximum age is the amount of seconds after receiving a BPDU before the root bridge port returns to a listening state. And the hello time is the amount of time, or in this case, seconds between BPDUs sent by the root bridge. Then we have the basic settings which are configured on the root bridge. The bridge address is the MAC address of the switch you're logged into. The priority is where we select the priority value. In the drop down, there are many from 4096 to 61440. And as I said, these go up in multiples of 4096. Just remember that 4096 is the highest priority. So if the switch is set to a lower value than the default 32768, and there are no other devices using the lower priority, then that switch will become the root. The maximum hop is the maximum of link hops a BPDU will travel from the root bridge. As long as the maximum age of the BPDU is not passed, the range is 1 through to 40 and the default is 20. The forward delay is the amount of seconds before the root bridge port rebuilds its bridge table after the maximum age limit has passed. The range is 4 through to 30 and the default is 15 seconds. The maximum age is the amount of seconds after receiving a BPDU before the root bridge port returns to a listening state. The range is from 6 through to 40 and the default is 20 seconds. The TX hold counts is the limit for the number of BPDUs that can be sent during a hello time period. The default is 6. And the hello time is the amount of seconds between BPDUs sent by the root bridge, which I mentioned earlier. The default is 2 seconds. So that's the default spanning tree settings. On the root bridge, you want to make sure that the root is in fact the root by checking the MAC address. That's really all we need to do on the root bridge for spanning tree and rapid spanning tree settings. Just make sure that is set to be the root bridge. Under the CIST or Common and Interface Spanning Tree, it's not required to be configured on the root bridge, as the Ethernet devices on the root bridge will be designated ports, and the root bridge is responsible for maintaining the spanning tree topology in the Ethernet network, and that includes the host connected to itself. You can set the port to be an edge port if you wish, so if there's a device such as a laptop, computer, a printer, or a games console, and is set to be an edge, this will improve the convergence time and the network performance, as those ports won't be part of any listening or learning phases. We consider port 11 and 13 are designated ports in a forwarding state. It's the 8-port switch that will be doing the calculations. Now, I'm going to go to my 8-port switch and check the global settings, and then the CIST settings, which need to be configured on the secondary switch. In my 8-port switch, in the spanning tree global settings, we see the settings on the root bridge information. I've got the correct root address, which is the MAC address of the 24-port switch, and the priority of the root is 4096. The cost is 20,000, which is a 1 gigabit link, and that's all fine. If I go to Advanced, STP, and CIST, we can now do some configuration. In the first column, I have the port number. Second, we have the priority. This determines the path to the root switch based on the cost. By default, all ports are set to 128, so the switch will determine the best path back to the root bridge. If I knew that port 1 was the root port back to the root bridge without going via another switch, I could set the priority to a lower value and tell the port that is the root port. So I've set port 1 to a value of 16 and port 2 to 32. Then we have the path cost configured and operating column. This is where you can manually set the path cost. Remember earlier I mentioned the long path costs. Our port is operating at 1 gigabit, so we can set the path cost to 20,000. However, if we leave it at 0, then we can use the operating path cost, which again is 20,000 or 1 gigabit. Designated root bridge displays the root bridge priority, followed by a /, then the forward delay, and then the MAC address of the root bridge. If this field says anything other than the root bridge priority and MAC address, then something's not quite right. So the external route cost, regional route bridge and internal route costs and designated route bridge refers to MSTP or multiple spanning tree protocol. MST allows the ability to map VLANs to different spanning tree instances and give the VLANs their own route bridge. So if your default VLAN had a route bridge on one switch, you can set the route bridge on another VLAN to be a different switch. When you configure MST, you give the instance of MST a region name, and the switches with the same region name are part of that same region. So configuration is key for reliable operation. So we have external route cost, which tells us the cost to reach the route bridge across links or paths that are outside of the spanning tree domain. The regional route bridge is the route bridge that's elected within a spanning tree region. If you're using MSTP, by where the VLANs can have a route bridge across switches, this column shows the priority, forward delay and MAC address of the regional route bridge. The internal route cost is the cost to reach the regional route bridge inside the MSTP region, and the designated bridge will display the bridge that's forwarding frames to the regional route bridge. So we can see that my 8-port switch can see the 24-port switch as the designated route bridge, and the regional and designated bridge is the MAC address of my 24-port switch, because I'm not using an MSTP setup. Then we have the edge port. An edge port is a switch port that has an end device on it that's not capable of switching and not capable of causing network loops, such as a TV, an IP phone, a printer, a games console, or an IP intercom, for instance. So this would be normally set to an edge port. Also, systems such as Sonos that have built-in switches on some of the players, or can use wireless to communicate among the players and re-enter the network, potentially causing loops, can be classed as a non-edge device. If a port is set to an edge port, it bypasses the STP convergence timers, so those end devices can connect much quicker to the network and not go through the listening and learning states with BPDUs and just forward traffic. So be sure that you set the correct host devices to be an edge port. As I said earlier, it's optional to set the core switch to have any edge ports, as they're all designated ports. So on the 8-port switch, we're going to set ports that the general Ethernet devices live on, such as edge ports. The link between the 8-port switch and the core switch are then set as a non-edge port. Then we have P2P. This is point-to-point. If you're interconnecting switches, that link is a point-to-point connection within the spanning tree configuration. Leaving it on auto will leave the switch to negotiate whether it's a full duplex link or not. A full duplex link would be between switches. But if it was something such as a legacy hub connected to the switch, that would be half duplex, hubs operated at half duplex. And this is where data can only be sent and received at any one time. I'll leave this as auto, but I'm going to set the P2P to yes on port 1 and port 2. Then we have the port roles and states: disabled, route, non-designated, alternate, and designated. Route is the path with the lowest cost back to the route bridge. Alternate is the link between bridges and is not the designated ports, and only comes into play if the designated port fails in an RSTP setup like ours. Then we have the port states, which we've just been over: disabled, blocking, listening, learning, and forwarding. And there we have it, a very basic spanning tree setup. You can see that in the 8-port switch, the route bridge is the MAC address of the 24-port switch. In CIST, the priority of port 1 is 16, high priority, and port 2 is 32. We can see that the designated route bridge shows the priority of the route bridge and its MAC address. Regional route bridge and designated route bridge is the priority and MAC address of the 24-port switch, the core switch. Then the port role is route and the status is forwarding. Port 2, we can see the same details, but it's an alternate role, a blocking state, and is discarding traffic. If I disconnect port 1, we will see port 2 take on the route role. I think that's a lot of information to take in for spanning tree, and MSTP configuration is another video. So thank you very much for watching, and I'll catch you on the next one.